Hello everyone, and welcome to a very special episode of Math-321. This is the Practice Test 2 solutions, and Practice Test 2 is going to be issued on April 3rd, 2020. Okay, so first let's go over the instructions just so we're all clear on how this is going to work. So I'm going to issue the test on Friday, April 3rd, and along with all of the homework and the journals and everything else, it'll be due on Friday, May 8th at 11:59 p.m. So that is the end of finals week. Okay, so from each of the 6 sections, I'm going to choose one similar question. So they're not going to be identical like last time, but they'll be similar. And that'll go on the real test. And the test will be open notes, open book, and open internet, including practice test solutions. So you can watch this video while you're taking the test, or you can look at the PDF of the solutions. However, the only exception really is that you cannot talk to anyone but me about the questions on the real test. So of course that also means you cannot ask people on the internet about the questions. So for all of these questions, I did not make the boxes like I did on the last test because it is open book and open notes. So you can just use anything from the notes or from any part of the textbook. That includes results of activities, as sometimes those are significant, and also homework problems. Unless the activity or the homework problem happens to be identical to the test question, in which case obviously you should not just cite that. You can also use your common knowledge of integer, matrix, and complex arithmetic if those happen to come up. I would like you to cite any theorems, corollaries, or results of homework or activities that you use when the result is not obvious. And of course that's subjective, but just for example, it's obvious that for integers a and b, that negative a times negative b is ab. So that would be something that you don't need to cite, although you could cite it. It's a result of activity 1.6. On the other hand, something I would think is not obvious is that 5a plus 7b equals 1 implies that the greatest common denominator of a and b is 1. So you would want to cite that as a result of corollary 3.11. And like I said, that's subjective, so just use your judgment, and you can ask me if you're not sure about what you should cite or not cite. Okay, so let's get right into the first section here, so Appendix A. Okay, so let's do the first problem. So problem 1, consider the function f from the integers to the integers defined by f of n equals 3n plus 2. So there's 2 parts. Part A, prove that a is injective, and part B, prove that f is not surjective. So I just put in the box up there on the right the relevant definitions and theorems and things like that for all of these questions. So that tells you how to prove that f is an injection. So let's go ahead and do that. So part A. Okay, so I'm going to prove that f is injective. Proof. Okay, so I'm going to let x1 and x2 be elements of the domain, so elements of the integers. And I'm going to assume, so we're trying to prove an if-then statement, so to prove an if-then statement, you assume that the if part is true. So I'm going to assume that f of x1 equals f of x2. Okay, so what I've done so far is I just replaced the for all with let, and then I copied that. And then instead of saying if, I'm going to assume, so I'm going to assume this if part here. And now this is the part that I want to show. Okay, so I'm going to try to show that. All right, so based on my assumption, I have that f of x1 equals f of x2. So that means I'm going to have 3x1 plus 2 equals 3x2 plus 2. And now I think it's pretty easy. You can see how we're going to be able to show that x1 equals x2. So I'm just going to cancel those, and I get 3x1 equals 3x2, and then I'm going to cancel those. And I have that x1 equals x2, and that's it. So it's not particularly difficult. So now let's look at part B. Okay, so for part B, I'm going to prove that f is surjective. So f is surjective, proof. Okay, so let's look at how we do this. So we need to show that there exists a value of y in the codomain. such that for all x in the domain, f of x does not equal y. So basically what I have to do is I have to find a value of the integers. So I have to find an integer such that f never outputs that integer. And you want to keep in mind here that 3n plus 2, when n is an integer, 3n plus 2 is always 2 more than a multiple of 3, but not every integer can be expressed as 2 more than a multiple of 3. Okay, so for example, like 3 is not 2 more than a multiple of 3, because 3 is a multiple of 3. So what I'm going to do is I'm going to say let y equal 3, which is in the integers. So I'm just pointing out that that's in the codomain. And then I'm going to say we will show there is no x in the domain, the integers, such that f of x equals y. And we're going to do this by contradiction. So suppose, to the contrary, that there is some integer x such that f of x equals y. And then I'm going to try to find a contradiction, okay? So if that is true, if f of x does equal y, then what we have is that 3x plus, I guess I should have used n, but I just went with x by default. So then 3x plus 2 equals 3. Okay, and then we can just do a little algebra on that and get that, so then 3x would equal 1, and then x would equal 1/3. Okay, but we suppose that x was an integer, so 1/3 is not in the integers, which is a contradiction. So since we got a contradiction, that means our supposition was wrong. Remember, our supposition was that there was some x in the integers that gave us f of x equals y. Was wrong. So there is no x in the integers such that f of x equals y. So f is not surjective. And that's it. Okay, let's look at number 2. So it's similar, but not quite the same. So we're going to do part A the same way. Notice here that the domain of this function is not quite the real numbers, it's the real numbers without 1, and that's because you can't plug 1 into that function because it would give you an undefined. But other than that, A is injective, and so we're going to prove that first. Did I say A was injective? I meant to say other than that, G is injective. So G is injective. Proof. Okay, so we'll do this the same way as before. So instead of saying for all x1, x2, I'm going to say let x1, x2, and then it's not A, it's our domain is the real numbers without 1. Okay, and then we're going to assume the if part here. So we're going to assume, and also it's not f, it's g. So we're going to assume that g of x1 equals g of x2. Okay, and then what we need to show is this, that x1 equals x2. Okay, so we're just going to use the formula. All right, so since g of x1 equals g of x2, that means that 2x1 plus 3 over x1 minus 1 equals 2x2 plus 3 over x2 minus 1. Okay, so now I'm just going to cross multiply. So I get this. Okay, and now I'm going to FOIL these. So let's see, I'll get 2x1, x2, 3x2, What else? So that was that and that. Okay, and then I need to give them both to the -1. Where's my eraser? Okay, so I'll make this negative 2x1, that's that one, and then this one -3. Okay, and then on the other side, I'm getting very similar result. So 2x1, x2, and then -2x2. For some reason I'm foiling in a different order this time, I don't know why. And then 3x1, and then -3. Okay, so anyway, once you've got that all foiled out, you can cancel some things that are on both sides, like the -3 and the 2x1, x2. And so then, let's see, what are we left with? So 3x2 minus 2x1 equals -2x2 plus 3x1. Okay, so now I'm just gonna move, I think I'll add 2x1 to both sides. Okay, so then I get 3x2 equals, so those cancel. And then on the right hand side I have -2x2 plus 5x1, and then I'll just add 2x2 to both sides. So I have 5x2 equals 5x1, and then, sorry, I've sort of run out of space here, but then we have that x2 equals x1. And that's it. Okay, so let's look at part B. So to show that G is not surjective, we're going to do it very similar to the last one. So we have to find some y in the codomain, which is the real numbers, such that no x in the domain produces that value of y. So in other words, for all x in the domain, f of x does not equal y. So you have to be kind of careful with this one because there is only one value of y that will work. And you might need to graph this, go to desmos.com or use your graphing calculator and actually graph this and try to see what the value is. But I'll just tell you right now it's 2. So 2 is the value of y that will not work, and you can look for that with a graph if you need to. Okay, so G is not surjective. Proof. Okay, so I'm going to let y equal 2, and then let's suppose there is some, so I'm just going right to the supposition that's going to give me the contradiction. So suppose there is some x in the domain, which is this, such that g of x equals y. Then, so what would that tell me? If g of x equals y, that would mean that 2x plus 3 over x minus 1 equals 2. Okay, so now I'm just going to do some algebra. So I'll cross multiply or multiply both sides by x minus 1. Okay, so then 2x plus 3 equals 2x minus 2. So I can eliminate x on both sides, and I get that 3 equals -2, which is a contradiction, obviously false. So that means our supposition was wrong. So there is no x in the domain such that g of x equals y. So that means G is not surjective. And that's it. Okay, so let's look at number 3 here. So this time we're going to prove that the function is not injective and is surjective. So this is the opposite of what we've been doing so far. So let's start with part A. Okay, so I'm going to prove H is not injective. I'm sorry, my cat is talking in the background. I hope you can't hear him. So proof. Okay, so what do we have to do to prove that something is not an injection? So what you have to do is you have to find two values, we'll call them x1 and x2, in the domain such that they are not the same value, so they're actually two different values, and they do produce the same output from the function. Okay, so I think when you look at this function here, I think it should not be too hard for you to think of two values of t that would give you the same value for h. So for example, like 1 and -1, or -2 and 2, those will give you the same output. Okay, so I'm just going to say let x1 equal 1 and let x2 equal -2. Then obviously x1 does not equal x2, but when we plug them in, we get h of x1 is 1 to the 4th, so that's 1, and h of x2 equals -1 to the 4th, which is also 1, so h of x1 equals h of x2. Okay, so that's all we need to show. That means that h is not injective. Okay, so that's part A, and now let's do part B. Okay, so now let's do part B. So for part B, we're going to prove that h is surjective. Okay, so this part is a little bit tricky because it involves doing some scratch work. So what you have to do is show that for all y in the codomain, there exists something called an x in the domain, such that f of x does equal y. So this there exists part, that's the part that's hard because you have to actually find a formula for what x would be in terms of y. So let me show you how to do this. So we're gonna let y be in the codomain, so let y be a positive real number. So then what we have to do is we have to actually find a formula for x that when we plug that formula for x into h, that it actually gives us y. So I think in this case, it's like not too hard to see that you should do the 4th root of y. But let me just show you how you would figure that out if you weren't sure. So let me put it over here in a little bubble, just to make it like abundantly clear that this is not part of the proof, because proofs do not involve little cloud bubbles. So this is some scratch work over here. So we want x such that h of x, and sorry, I'm just using x instead of t, I don't know why, such that h of x will equal y. So what we need then is that y equals x to the 4th. So basically then you just have to solve for what x would be. So I'm just going to solve for x. Okay, so all I have to do is just take the 4th root of both sides. Now keep in mind there's a couple of things that could go wrong here. So first of all, y has to be positive in order for this to work because we're taking an even root of it. So if y were negative, this would not work. Also keep in mind that when you do the even root of an even power like this, that you really get plus or minus the 4th root of y. Okay, so either the positive or the negative version would work. Now in this case, we definitely need to take the positive version because our domain only contains positive numbers. Okay. But either of those, if it were a different situation, either of those would work. Okay, so that's our scratch work. So I'm putting it in its little cloud bubble to make it clear this is not part of the proof, it's just scratch work. And so we're going to let x equal the 4th root of y. Okay, now we need to argue that this formula for x will actually be in the domain. So then x is going to be in the domain, which is the positive real numbers, because y is in the positive real numbers, basically. That's all you really need to say. Okay, So it's pretty obvious. I hope that, you know, the fourth root of any positive real number will also be a positive real number. I don't think you need to really prove that. That's pretty obvious. Okay, so then what you need to show is that h of x will actually give you y. So you need to actually plug in your formula for x into the function and show that it really gives you y. So this is going to be fourth root of y to the fourth, and that is going to be y. Okay, so this means that h is surjective. So for any value of y in the codomain, we have a way to find a value of x in the domain that produces that value of y. And that's it. Okay, so let's look at the next problem here. So, number 4, let f be a function from a to b, and let g be a function from c to d, and both f and g are going to be injections. And then let h be a function from a cross c, so the Cartesian product of a and c, to b cross d, the Cartesian product of b and d, that is defined by this formula here, where when we input the ordered pair AC to H, the output that we get is the ordered pair of f of A and G of C. And that's for all possible elements AC in the domain, which is A cross C. So we need to prove that H is an injection. Okay, so this might seem a little weird, but we're just going to go about this the same way that we always go about proving that something is an injection. So I'm just going to do it the same way as usual. I'm going to let there be two elements x1 and x2 in the domain, and then I'm going to assume that they have the same output from the function, and then I'm going to prove that they must have been the same element. Okay, so let's just give it a try and see how it goes. So proof. So let x1 and x2 be elements of the domain of H. Okay, so here's the first place where it becomes a little bit weird. So x1 and x2 are elements of this Cartesian product A cross C. So I think rather than just calling them x1 and x2, which are like typical element names, I want to actually call them, or I want to write them in a form that makes it clear that they are ordered pairs. Okay, so I'm going to back up and I'm going to do that. So I'm going to do it like this. Let x1, I don't know, I'll just call it y1, and x2, y2. So I'm going to call my two elements of the domain like this, because this makes it really clear that they are actually ordered pairs, and then this will give me more to work with. Okay, I had to pause the recording there for a second to take care of my cat, so I'm not sure where I was. But alright, so we have two elements that are in the domain here. So they look like ordered pairs because the domain is ordered pairs. And so now we're going to go ahead and we're going to assume that if part of the statement, so that the output from the function is the same for these two ordered pairs. So we're going to assume that h of x1, y1 is equal to h of x2, y2. Okay, so what does that mean? So that would imply, or that would mean, that f of x1, so I'm just using the definition of the h function here, comma g of y1 equals f of x2, comma g of y2. Okay, so whenever you have an ordered pair equaling another ordered pair, that means the first elements are equal and the second elements are equal. Okay, so f of x1 equals f of x2, and g of y1 equals g of y2. Okay, so now that we have that, we can use the fact that f and g are injections. Okay, so since f and g are injections, that implies that whenever you get the same output from an injection, it must have been because the inputs were the same. So that means that x1 equals x2, and y1 equals y2. And so for us, what's important about that is that means that these ordered pairs, x1, y1, and x2, y2 are the same ordered pair, which is what we were trying to show in the first place. Okay, so that means that H is injective. And that's it. Okay, so let's look at number 5 here. So let R from y to z and S from x to y be functions, and let R composed with S be an injection. Prove that S is an injection. So this is a little bit of an unusual question, but I'm just going to approach it the same way I always approach proving that something is an injection. So in other words, proof. I'm going to let x1 and x2 be elements of the domain of S. So in other words, be elements of X. And I'm going to assume that they give the same output from S. So in other words, assume that S of x1 equals S of x2. And then I'm going to try to show that x1 equals x2. So at this point, I would usually plug those values into the formula for S. But since there is no formula for S, I'm going to have to do something else. So the only other option I really have here is to use the only other fact I know, which is that R composed with S is an injection. Okay, so that's what I'm going to have to use. So how am I going to get R composed with S into the situation here that I have so far? Well, what I could do is I can plug both sides of this equation into R. So then I would have R of S of x1 equals R of S of x2. Or in other words, I have R composed with S of x1 equals R composed with S of x2. Okay, and now what can I do? Well, I know that R composed with S is an injection. So whenever an injection has the same output, it must have been because it had the same input. Okay, so because R composed with S is an injection, that implies that x1 equals x2. And that's it. I showed that x1 equals x2. So S is an injection. Okay, so that was everything from Appendix A, and now let's look at some questions from Investigation 21. Okay, so number 6, let G be a group with identity E, and let A and B be elements of G. Prove that if AB equals E, then BA equals E as well. Okay, so I put in the box over here the relevant facts that you might want to keep in mind for this question. So we have the fourth group axiom about inverses in groups, and we also have the group cancellation law. Okay, so let's see if we can apply these. So I'm going to do my proof here. Okay. So I'm going to go ahead and assume, or I'm just going to copy down the things that were in the statement. So let G be a group with identity E and AB are in G. And I'm going to go ahead and assume the if part of that if-then statement. So I'm doing a direct proof. And then I'm going to try to show the then part. So I want to show this. Okay. So what can I do here? Let's see. Well, I have that A times B equals E. And normally the only time you get E from multiplying two elements together was if the two elements were inverses. So what I'm going to use is the fact that I'm going to just say it like this. So since G is a group, A has an inverse, and I'm going to call A's inverse A inverse, like that, such that A times A inverse equals E. So that's just a definition of an inverse. And then based on the fact that both AB equals E and A inverse equals E, that means that AB equals A A inverse. Sorry if you guys can hear my cat squeaking. He's a very, he likes to let me know how he feels. So then we can use the group cancellation law. Use theorem 20.7. So this might be an instance where like this is kind of optional. Like you can cite theorem 20.7, or you can just assume that it's obvious that things cancel in groups. That then we can cancel it and we get that B actually equals A inverse. Okay, you could have just gone straight there from the fact that A times B equals E to just immediately say that B equals A inverse, but I just wanted to make it clear to you why that is the case. Okay, so B is A inverse. So that means that B times A equals A inverse times A, which obviously is going to equal E. That's another definition that you get from the definition of inverses. Okay, so we did it. That's it. Okay, so let's look at number 7. So let G be a group with the property that for all AB in G, AB squared equals A squared B squared. Prove that G is abelian. Okay, so over here on the right, I just put the things that might be relevant here. So like if you forgot what abelian means, that's over there as well. Okay, so let's go ahead and do this. So proof. So I'm just going to copy the things that were in the statement. So let G, oops, not that G. Let G be a group such that for all AB in G, AB squared equals A squared B squared. Okay, so in order to prove that G is abelian, what we need to show, so we will show that for all AB in G, AB equals BA. So I'm just putting that in brackets because that's like an optional kind of goal statement there for you. That's definitely what we need to do. You just don't need to necessarily put that in your proof. You just need to do it. Okay, so in order to do that, I'm going to let AB be elements of G. Okay, well, what do we get from that? So we get the fact that AB squared equals A squared B squared. And what we need to do is we need to show that AB equals BA. So how am I going to do that? Well, I'm going to try to, I think, extract or make AB appear by itself on one side of this equation. So you can't take the square root of both sides, for example, because this is not the integers. But you can still do something. So let me show you what you can do. So since we have AB squared, that's the same as AB. So I can write that. And then what I can do is I can multiply both sides by B inverse or A inverse as much as I want to, because it's a group, so those inverses exist. So what I'm going to do is I'm going to multiply both sides on the right by B inverse. Okay. B inverse. Okay, so when I do that, this B and this B inverse here cancel, and then this part here, this B squared B inverse, that's gonna just become B. Okay, so what I get now is ABA equals A squared B. Okay, and now I really want to make AB just appear by itself on the left. So I'm gonna multiply on the right by A inverse. Okay, so let me do that. I'm sorry, my cat has just like jumped in my lap and he's purring and like pushing his face at me. So I'm just trying to keep writing this equation, even though this cat right here. Maybe you guys can hear him purring, I don't know. All right, so AB, oh my gosh, okay, I have to pause this. Okay, so while I had the recording paused, I saw a better way to do this, so let me back up and do something different. Okay. Okay, so what I want to do now, I think, is actually rather than make AB appear on the left, I want to make BA appear on the left. So I'm going to multiply both sides on the left by A inverse. So like this. And you're going to see why this works in just a second. Okay, so those are going to cancel out, and then this part here is going to become just A. Okay, so that is actually going to give us exactly what we want. BA equals AB. And that is it. Okay, so let's look at number 8 here. Let G be a group with identity E, and let A be in G. Okay, so I'm just going to copy those statements into my proof. So let G be a group with, just abbreviating, identity E, and let A be in G. Okay, so we're going to prove that if b to the 6th equals e and a times b equals b to the 4th a, then b cubed equals e and ab equals ba. Okay, so I'm doing an if-then statement proof, so I'm going to go ahead and assume the if part. So assume b to the 6th equals e and ab equals b to the 4th a. Okay, so this problem is actually a little bit tricky. But let me show you how to do it. So I'm going to use this statement here first, the second equation first, and move a term around, or move the a on the right-hand side to the left-hand side, or in other words, I'm going to multiply both sides by a inverse. So since ab equals b to the 4th a, we can say a inverse. So I'm going to multiply both sides by a inverse, and you have to be careful because this group is not commutative, that you multiply on the right hand side on both sides, or that you multiply on the left hand side on both sides. Okay, so now that I've multiplied by a inverse, it cancels out here, so that's going to equal b to the 4th. Okay, and now what I'm going to do is like really kind of hard to think of doing, but let me show you what I'm going to do. So I'm going to take this and raise both sides to the 4th power. So raising both sides to power 4, we get the following. So we get a inverse to the 4th equals b to the 4th to the 4th. Okay, so again, this group is not abelian, so you have to be very careful that on the left-hand side you do not distribute that 4th power to both a, b, and a inverse. Instead, you want to write this like this: a, b, a inverse, a, b, a inverse, and then just 4 times a, b, a inverse, a, b, a inverse. Okay, and then on the right, it is going to be b to the 4th, b to the 4th, b to the 4th, b to the 4th. But if it's just a single element like b, you can actually multiply those two exponents and just get b to the 16th. There are some rules to that effect. Unfortunately, I did not put them on this slide, although I think they're on a later one, as well as, of course, in your notes and your textbook. Okay, so what can we do with this? So just continuing to put words here that mean I'm simplifying. So I can actually cancel this a and this a inverse, a and a inverse, a and a inverse. And so what I'm going to get here is, let's see, so I have a, and then I have b, 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 b. So that's b to the 4th. And then I have a inverse. And then I have that equals b to the 16th. Okay, so now at this point is where I'm going to use the fact that b to the 6th equals e. So since b to the 6th equals e, we can say, so let me do it like this. So a, b to the 4th, a inverse. So I'm going to write b to the 16th as b to the 6th, b to the 6th, b to the 4th, because those add up to 16. So I can say that that equals b to the 6th times e, which is just b to the 6th. Oops, excuse me, this should be actually a 4, right? And so this should have been actually e there, and then e there, and then b to the 4th there. Okay, sorry about that. So that is going to be b to the 4th. Okay. Okay, so what we have so far is we have a b to the fourth, a inverse equals b to the fourth. Now remember that previously we also had that a inverse equals b to the fourth. So I'm going to use that. So since a inverse equals b to the fourth, we can say that a b to the fourth, a inverse equals a inverse. Okay, and so now what I can do is I can use the group cancellation law. So using theorem 20.7, I'm going to cancel the a's on the left side of both sides, and on the right, and I'm going to cancel the a inverse on the right side of both sides, like this. And so I get that b to the fourth equals b. And so again, I can rewrite that in the following manner, which is equivalent to b cubed times b equals b. And again, I can cancel or multiply on both sides by b inverse. So that yields b to the 3 equals e. So when I cancel those b's on either side, I get e on the right, not nothing. Okay, so, all right, I'm halfway there. I got b cubed equals e. And now to show that ab equals ba is not very hard. So I'm just going to use the fact that, so going back to the original problem statement, ab equals b to the fourth a. That means ab equals b cubed ba. So I'm separating the fourth power there, which is the same as ba, which is the same as ba. So ab equals ba. And that is it. Okay, so let's try this problem number 9, and this one is actually a little bit tricky. So for my proof statement, let me just copy the let statements. So let G be a group such that for all AB in G, AB cubed equals A cubed B cubed, and AB to the fifth equals A to the fifth B to the fifth. Okay, and we have to prove that G is abelian, and we cannot rely on any other equations other than these, so we're going to have to do everything from these. Okay, so let me start by using this equation right here. So since AB cubed equals A cubed B cubed, that means AB, so that's AB cubed is AB. In this group, we have not shown that it is abelian yet, so we cannot move those A's and B's around each other, equals A, and then I'm going to split off one A and then have A squared, and then I'm going to do the same for the B's, but I'm going to leave one B on the end like that. So I split the cube into A and A squared, and the B cubed into B squared and B. So using theorem 20.7. Okay, so theorem 20.7 says that we can cancel things in groups. If we have the same element on the right, we can cancel it like this, or if we have the same element on the left, we can cancel it like this. So we're going to do that here. So we get, so what's going to cancel here? So I'm going to cancel an A on the left on both sides, and I'm going to cancel a B on the right on both sides, like that. So we get that BA equals A squared B squared. So another way to say that would be to say BA squared equals A squared B squared. Okay, so now that I have that, I'm going to try doing the exact same thing with my other equation, this one. So since AB to the fifth equals A to the fifth B to the fifth, that means that AB AB. You know what? Actually, I don't think I need to write them all out. I think I just need to, I could put those three together like that. And then just have one AB on the left and one AB on the right. And then that is going to equal a to the fifth, b to the fifth, which is also equal to a to the fourth, b to the fourth, b. Okay, and then using theorem 20.7, I'm going to do some cancellation. So we get, all right, so what cancels out here? So I'm going to cancel 1a here and 1a here, and I'm going to cancel 1b here and 1b here. So what I get is that b ab cubed a equals a to the fourth, b to the fourth. And now I think I actually want to write out that left-hand side a little more fully, and I'll show you why. So this is going to be b, ab, 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 and then another A, and then A to the fourth, B to the fourth. Okay, so the reason is because I wanted to write the left-hand side as BA to the fourth. So BA to the fourth equals A to the fourth, B to the fourth. Okay, so far what we have are these two. BA squared is A squared, B squared, and then BA to the fourth is A to the fourth, B to the fourth. And what is actually useful about that is that BA to the fourth is the square of BA squared. So what this tells us is that, so using BA squared equals A squared B squared means, or rather tells us that, so BA squared squared, so if we square both sides, we get the following. So that gives us, that implies that BA to the fourth, so I can combine the two squares there because they're on the same element, which is BA. BA to the fourth also equals A squared B squared squared. And we already knew that BA to the fourth also equals A to the fourth, B to the fourth. So that means that A squared, B squared, squared equals A to the fourth, B to the fourth. Okay, and now I'm going to write out that equation a little longer and cancel some stuff. So I'm going to write that out as A squared, B squared, A squared, B squared, and then I'm going to write the right-hand side as A squared, B squared, B squared. Okay, and then I'm going to cancel these A squareds and these B squareds. So that tells me that B squared, A squared equals A squared, B squared. Okay, all of that work that we just did was to get this equation. Okay, so now that we have this very important equation right here, we're going to go back to the beginning. So going back to AB cubed equals A cubed B cubed. We can write that right-hand side as the following: A times A squared, B squared, B. And then what I'm going to do is I'm going to substitute for this part right here. A squared, B squared, I'm going to substitute there for B squared, A squared. Okay, so this is going to be A, B squared, A squared, B. Okay. So that implies, so I'm going to write out AB cubed, and I'm going to write out this last part here. So that implies AB equals, and I'm going to write the whole thing out. So A, B, B, A, B. That's this part right here. Okay, and now I'm going to do some cancellation. So let's see what I can cancel. So that implies, so I can cancel an A in the front, and then after I've canceled that, I can cancel a B. Okay, and then on the back side, I can cancel this B, and then I can cancel this A. Okay, so what am I left with? I'm left with AB equals BA. And that is it. And that one is quite a challenging problem. I think I actually worked on it for about half an hour before I finally gave up and looked up how to do it on the internet. Yeah, so that's that problem. Okay, so first of all, number 10, let H and K be subgroups of a group G. Prove that H intersect K is a subgroup of G. So here by the intersection, we just mean the same thing as we usually mean by the intersection. In other words, this is all the elements that are in both H and K. Okay, so let's go ahead and try this. So I'm just going to copy down the let statements. Let H, K be subgroups. I'm abbreviating subgroups like this of G. Okay, so let's consider the intersection of H and K. So I'm going to break this down into the three things that I have to show here. So part I, we will show, I'm just going to put a goal statement here to kind of keep myself focused. So we will show H intersect K is closed under the group operation, whatever that might be. I'm just going to write it as multiplication since I don't know what it is. Okay, so this is an optional goal statement. So in order to do what I just said, we're going to let, let's call them A and B, be elements of H intersect K. Okay, so what do we get from that? Well, then A comma B are elements of H, and A and B are elements of K. And then since H comma K are closed, that would mean that AB, so A times B in other words, is an element of H, and A times B is an element of K. So A times B is an element of H and K, or H intersect K. Okay, so H intersect K is closed. All right, that's good. So that was the first one. All right, let's do part 2 here. So we will show that that E is in H intersect K. Okay, this is probably the easiest one. So since H comma K are subgroups, we have that E is in H and E is in K. So E is in the intersection, because all subgroups contain the identity. Okay, that was easy. All right, let's see if part 3 is also easy. So we will show H intersect K contains inverses. Okay, so let's say that A is in H intersect K. Then we need to show that A inverse is in there. Okay, so since A is in H, that means that A inverse is also in H, because H is a subgroup. Sorry, this is a little sloppy. Okay, and since A is in K, A inverse is also in K for the same reason, because K is a subgroup. So A inverse, since it's in H and it's in K, it's in H intersect K. Okay, so we showed all 3 properties. So apparently the intersection of 2 subgroups is always a subgroup. It's interesting. Okay, let's look at number 11. So here, recall that the center of a group is denoted Z of G, and that is all the elements A in G, such that AG equals GA for every element G of the group. So in other words, the center is all the elements that commute with everything in the group. So let G be a group and let A and B be elements of G. Prove that if AB is in the center of the group, then AB equals BA. Okay, so this is kind of interesting. So we don't have that A and B themselves are in the center. We only have that AB is in the center. So let's see what we can do with this. So proof. So I'm just going to do the let statements again. So let G be a group and let A comma B in G. And then I'm just going to do a direct proof. So I'm going to assume the if part is true. So assume AB is in Z of G. Okay, so now I'm going to try to show this part here, show that AB equals BA. Okay, so all I really have to work with here is that AB is in the center, so that means AB would commute with any element in the group. So I just have to kind of like cleverly try to think of a good element for it to commute with that would be helpful to me. And so let me try the following. So then since AB commutes with all elements of G, that would mean that AB times B inverse, so AB would commute with B inverse, so that would mean that this would equal, no, wait a minute, that was right. Then I can put B inverse times AB like that. Okay, so that's AB commuting with B inverse. So that would tell me that A equals B inverse AB. And I think that's actually, yeah, that's exactly what I want. Then if we multiply, then by multiplying by B on both sides, we get, so I'm just going to take this one and multiply B onto the left on both sides. BA equals B inverse AB. So that would implies that BA equals AB. Okay, so that's it. All right, not too bad. Okay, so let's look at the next one, number 12. So let H and K be subgroups of an abelian group G, and let H times K, or HK, be all of the elements AB, such that A is in H and B is in K. So it's just literally all the products of things from H with things from K in that order. Prove that HK is a subgroup of G. Okay, so let's give this a try. Proof. I'm just going to repeat all the let statements. Let HK be subgroups of abelian group G. Okay, let HK equal this. Okay. So, how are we going to do this? So we need to do the three parts again. So we need to prove that H is closed. So we will show H is closed. Okay, so to show that that HK is closed, rather. Okay, so to show that HK is closed, let A comma B, actually, let me not call them that because we already used those letters. What else should I call them? I don't know, XY. So let XY be elements of HK. Okay, so what I want to show is that X times Y is also in HK. So all I know about X and Y from this assumption here that they're in HK is that they have the following form. So X would equal, let's call it A1, B1, and Y would equal A2, B2 for A1, A2 elements of H and B1, B2 elements of K. So everything that's in HK is supposed to have this form like this. Okay, so then what is xy going to be? So then xy would be A1, B1, A2, B2. And then since the group is actually abelian, that means I can rearrange this like this. So this will be A1, A2, B1, B2. And then furthermore, since H and K are subgroups, they themselves are closed under multiplication. So that would mean A1, A2 is an element of H, and B1, B2 is an element of K. So that would imply that xy is in fact in H times K, because we've expressed it as the product of an element of H times an element of K, where this is the H element and this is the K element right there. Okay, so HK is closed, and now let's do part 2. So we will show that the identity element is in HK. Okay, this one I think is really easy. So the identity equals E times E, where one of those E's is in H and the other one is in K. So we can write the identity as the product of an element from H times an element from K. Right, so E is in H times K. Okay, I hope that made sense to you. And then part 3. So we need to show that we have inverses. Inverses. Okay. So let's consider a generic element in, I'll just call it X again. Let X be in HK. Okay, so then X has the form AB for A in H and B in K. Okay, so then we know that A inverse is in H and B inverse is in K. So that would mean A inverse, B inverse is in HK, but that's not actually the inverse of AB. The inverse of AB is B inverse A inverse. But since the group is abelian, G is, oops, sorry, I've kind of run out of room here. Like trying to write on top of the controls. Since G is abelian, A inverse B inverse equals B inverse A inverse, which is the inverse of AB. Okay, so that means that the inverse of AB is in HK. Okay, and that is it. Well, I guess I should say that's, that means that the inverse of X is in HK, since that's what we started with. Okay, so that is it. All right. Okay, so let's look at number 13. Let G be an abelian group and N a positive integer. Prove that H equals, prove that this set here, H equals elements A in G, such that A to the N equals E, is a subgroup of G. Okay, let's give this a try. So, I'll just copy my let statements. Let G be, that doesn't even look like a G, I'm sorry. Let G be an abelian group. Let N be a positive integer. Okay, Then we're going to prove this. So I guess I'll just let H have that definition there. A to the n equals E. Okay, so let's prove these three parts here. So 1, H is closed, so I'm going to let two elements be in H. So I'll call them A and B. Okay, so what do we know about A and B? Well, they're in H, so that would mean that A to the n equals E, and B to the n equals E. Okay, then I want to know, is AB in H? So what is AB? AB would be, well, I'm not exactly sure what AB would be, but in order to prove that AB would be in H, what I need to do is show that AB to the n equals the identity. So let me just try doing that. So AB to the n, can I simplify that at all? So based on the fact that G is abelian, I am actually able to distribute that n part. Okay, so whenever your group is abelian, you can distribute an exponent like that, but only when the group is abelian. So I'm gonna just note that that's because G is abelian. That's somewhere in the notes, but I failed to put it on this particular slide. Okay, so AB to the n equals A to the n, B to the n, because G is abelian. So AB to the n equals A to the n, B to the n, each of which is E, so this is E times E, equals E. So that means that AB is an element of H because it satisfies the membership test for H, where its nth power is the identity. Okay, so H is closed. All right, does H contain the identity? I think that's pretty clear because E to the n equals E. Okay, and let's look at the third thing we need to check here. Inverses. So let's see. Let's think about what is, sorry, let me actually rather start with letting A be an element of H, and let's think about what is the nth power of A inverse. So then A inverse to the nth power, what would that be? So this is another one of those rules from, I think, Investigation 21 maybe, that you can rewrite like this, equals A to the n to the negative 1, like that. So that would be E to the negative 1, which is E. So we assumed A was in H, so that means A to the n equals E. Okay, so A inverse does pass the membership test for H, so A inverse is in H. Okay, so we passed the three conditions for H to be a subgroup.